Hey fifth graders! Today your goal is to learn about inclined planes and screws. Your job is to think about how the distance that something goes on an inclined plane and the steepness of the inclined plane or ramp will affect how much work you're actually doing. You'll also learn about a screw because screws are inclined planes wrapped around a pole. So again, the longer that inclined plane is that's going around the screw, the amount of work is going to be affected by that. Now let's take a look at an inclined plane that I have here. So I'm going to put my camera down and you can see here that I actually have a ramp. It's a board that is going from the sidewalk up to my front step. So an inclined plane helps us with going from a lower point to a higher point, or of course back down. Now if I have it really at a gentle slope, right, we can think about how easy it would be for a car like this toy car here to go up or of course back down, right? And if we have it steeper, it's going to affect how easy it is for that car to go up and down. All right, so let's get started. We're going to first just set it right here. And I noticed that my car is going to start way over here, way by my pen. You see where my pen is? There you go. And it's going to travel this far. Now I'm going to write on this board. This is just an old board, not a big deal. So for it to go the height of this step, it has to travel all that way. I could even measure how far that is with my tape measure. And that distance is 96 centimeters. So it has to travel 96 centimeters in order to make it up that one step. I'm going to write that down. So it's going to go 96 centimeters. And now I'm going to find out how much effort it takes to pull the car up that ramp. So I'm going to put, here we go. So I'm going to put the spring scale right here. See, it's holding the car, and I'm going to drag the car up the ramp using the spring scale, and I'm going to see what the spring scale says. Right now, first, make sure that's on 0. It is. There we go. How many newtons of effort does it take? So I'm going to drag it, and my spring scale the whole entire time says it's taking 0.2 newtons, not even 1 full newton. So I'm going to write that down. So it took 0.2 newtons. That's a decimal point in front of there, right? I could even put a 0 in front. And let's label this. So the amount of effort it takes, here's my effort, and here's the distance it is traveling. Here's the distance. So now the ramp is slightly steeper. If I measured that angle, I would find that it's, instead of it being as gentle, it's a little bit steeper now. But notice we're going a lot less distance. So I'm going to draw that line here again. And I am going to also measure it. Let's see, this distance, now it's only going to travel 62 centimeters. Jackson, can you help me? My assistant's going to come over and help me now too. 62 centimeters. Split up, and we're gonna read how much force it's taking. And now instead of taking only 0.2 newtons, my spring scale showed 0.4 newtons. So we're going less distance, but it took more force. Now, this is where Jackson is going to help me, because in order to make my ramp stay still and not pop up like this, so now I have it even steeper. I'm going to mark where it is. Notice it's much shorter. It's a much shorter distance. It's only going to go only going to go 39 centimeters. Remember, the first time it went 96 centimeters. Second time we had to go 62 centimeters. Now it's only 39 centimeters. So the distance is getting shorter. But what do you think is going to happen to how much force it takes to make the car go up the ramp? Bet you're thinking for a second. All right, now this time, you're gonna help me? Yeah, okay, so Jackson's holding it still over on the other end just to make sure. All right, and then pulling it up. And now it increased, I bet you're not surprised, by another 0.2. It's almost like we're counting by 0.2 or 2/10. So now it takes 6/10 newtons. So it's requiring more effort, but the distance becomes less. We're gonna make it as steep as we can. There we go. I think that's pretty good. Hold it there. I'm going to put my foot there as well, just to help it stay in place. I'm gonna make a little mark there. Now, let's see how far it needs to go. So it's going to go from 0, it's going to go 23 centimeters, that distance. So now let's go ahead, we're gonna go ahead and drag it up. And this time, it says not just 0.8, it says 0.9. It's very close to 1 full Newton. So it's 0.9 newtons of effort, right? So the steeper the ramp or inclined plane becomes, it's less distance, but it requires more force. All right, so the next step of this is to think about how a screw is an inclined plane that is wrapped around a pole. And if the inclined plane that is wrapped around the pole is shorter, how that is going to affect the amount of work it takes to screw in that, let's say the screw, into a piece of wood. Now, this one's longer, but the actual inclined plane ends at almost the same point as this one. So that's why we're going to compare these two. It was as best as I could find in my garage. So we're going to use these two, and we're going to see how the inclined plane of this one is can compare to the inclined plane of this one. All right, so let's start. I have a string, and using this string, I am going to wrap this string around the screw from the top to the bottom. All right, now, there we go. I've got it going. And we're gonna see just how long the inclined plane is by wrapping the string along the inclined plane, right? So this whole time it's following the inclined plane, right? It's as if it's a tiny little ant going down, whoops, the inclined plane, there we go. So I have, this is where the top was. I'm gonna unravel this now, and we're gonna see how long the inclined plane is that's going around this silver screw. There we go. Sorry, I have it off screen because I'm trying to get it off. There we go. That is how long that inclined plane is. Now I can measure it as well. It is 29 centimeters long. So that inclined plane that is going around that screw, the silver screw, is 29 centimeters long. Now, on the other hand, let's have it go around this one instead. So again, I'm going to hold it on the end. There we go. And I'm going to wrap it around, again, following the inclined plane. Follow, follow, follow. And this one, I do not need to make it go around as much right now. All right, now I'm gonna hold the end. I have the other end. I'm gonna unravel it. Okay, unravel. There we go. It's only this long. Now, hopefully you can tell just by looking at it that that is much shorter. So I'm going to hold it up to my tape measure again. And this is only 16 centimeters. It's about half, right? 16 is not quite half of 29, but it's close, right? So this inclined plane of this screw is about half the length of the other one. So it's less distance that it has to travel when it's going into something. But I also learned, from what we learned before, that means if it's less distance, it's going to require more effort or more force. So I might have to make it go around fewer times. It's going to go less distance, but it might feel a little harder. It might take more muscle compared to the other screw. This one, I have to turn this one way more. The inclined plane is way longer, but it's going to feel like less effort, right? It's going to feel like less force.